That's what I work on. I work on drones, and I've been interested in applications to structural inspection, digital asset management. You can see my students credited there. Professor Jikyang Chen is at Kansas State. He's been a colleague in our peer-supported project. So we are working on these autonomy technologies, and so we try to collect examples of damaged structures. The first one was at the Big Press in Pier, where we were part of this test where a column was cracked. And then we collected this data about this church, Jefferson Church. It's damaged in Jefferson, Missouri, I believe. And then we looked at this long Japanese viaduct with cracks, because some people, you can see the people cited there from Professor Spencer's group also looked at it, right? So we're trying to, create and work on the same benchmark problems. Basically, what we do, the whole idea is to use so most people who utilize drones have a drone pilot or somebody dedicated to the use of drones. And so this is like the early days of a computer, where people were hired just to work for the computer. So there used to be a job, data entry operator, right? And people used to get hired to enter data into computers, but this is no longer the case, where everybody who works in an organization is expected to use a computer. We are trying to get drones to autonomously collect data, and then there's a layer on top of it that you can work on the detection of cracking, spalling, exposed code, like the previous speaker was saying, and there's been a lot of work on that, right? But this is sort of high fidelity reconstruction and image processing. You can't do the same fidelity of image construction and processing when you're trying to guide a drone, because that kind of processing can only be done offline. You have to do something much more crude to be able to guide the drone while it's doing things. So actually, let me go to the slide after this. So we basically, we're trying to enable autonomy. So again, in the bridge thing, right, that column-based thing, that's exactly what that group did, where they autonomously image the columns. We are trying to do more general shapes, so that it's not tied to one specific shape. I myself did some work there many years ago on using a drone to autonomously image and inspect a road. We later autonomously imaged and inspected an aqueduct. That was basically the inspection of locally linear structures. So we could come up with a way of, the problem is again, in real time as the aircraft is flying, how do you recognize what you're looking at well enough to at least gather the data about it, so later offline it can be reconstructed and thought about to higher fidelity, right? Is that clock working? It says 2:24 and it's stuck there.
No, don't worry,
okay.
I'll give you some.
Okay. And then, and there are other things where, for example, that wall one, it gets autonomous when it comes close to the wall because you have to avoid collisions. But other than that, it's flown manually, right? So this is our performance specification of the problem. So essentially 2R there is the resolution specification. So we want to image a structure to a particular resolution, right? That we assume comes from the application, from the depending on what you want to detect. And we transform that 2R into, so we say if we are imaging a 3D space, we imagine it as composed of cubes of R by R by R, and then 2R twice. So we basically we're using a LiDAR, we want one LiDAR return from each box of size R, right? So this means that the resolution specification is 2R, because if something is, if you have two boxes and you get one return from this box of size R and this box of size R, this return could come from this end of this box and this return could come from the other end of the adjacent box. So something up to size 2R could get missed, right? So by the resolution specification, I mean if something is smaller than 2R, then you don't care about it, right? Then other specifications are, of course, finally, this drone will fly and collect a point cloud, and then that point cloud can be used for 3D reconstruction or image analysis. And then we look at the error there. That's the offline error, right? And ultimately you want that to be good enough. And then the other thing we look at is completeness, that whatever is reachable in the bounding box which specifies the thing to be structured is actually reached, and whatever is observable is actually observed. So this picture gives you an idea of what we mean by reachable and observable. So the state of the inspection looks like this. The drone takes its volumetric construction and partitions it into boxes that are known to be occupied, boxes that are known to be free, boxes that are observable but unknown, right? The drone believes that, and then boxes that are unobservable and unknown. So for example, if you have that black space surrounded by blue spaces which are filled, then the drone cannot get to the black space, right? So that's an example of, it's an unobservable space, and of course it will remain unknown. So completeness means basically being able to make all of the observable known, right? So the solution that we use is essentially one that is a hierarchical planner and control. So this is where I would have reviewed the robotics literature. So a lot of the algorithms here are essentially have starting points in the robotics literature, which we then take and adapt to this purpose. So the reconstruction that's done, right, that volumetric reconstruction of which cubes are occupied, which cubes are free, which cubes are observable, which are unobservable, etc., is essentially something that's a variant of a SLAM algorithm, but it's a modification that enables it to be done fast enough so the drone can do it while it's flying, right? So that's done at about a 1 hertz rate, 1 second. And then there's a lower level control, which is a higher frequency control running at about 10 hertz, whose job is essentially to do collision avoidance. Right? So the higher level planner might say something and the lower level planner may produce modifications to it, and sometime of course the lower level planner might say, I'm not going to execute this at all because it's considered unsafe, in which case the main thing of putting a hierarchical control together is that because the lower level can override the higher level, it mustn't deadlock though, that the higher level keeps saying something and the lower level keeps saying no, and the system stays stuck there, right? So we've ensured that that correctness property is there, that it won't deadlock. And then, it terminates whenever the search is complete, in the sense I was explaining earlier. Here is an example with this Jefferson City thing, right? So we are also, I did a bunch of work for the Navy before this on multi-drone control, right? So the whole idea, of course, is to be able to use a fleet of these things to deal with inspection problems at scale. And here you're seeing 3 of them working on this Jefferson City Church in Missouri and flying and collecting different images that can then get stitched together, right? And this volumetric reconstruction though is synchronized. That's a small amount of data, so you can actually synchronize it in online as the aircraft are flying, so they can keep reallocating and replanning themselves. So what we've essentially done here is the validation is by simulation, right? The validation of the autonomy. So of course, in practice we go fly the drone at the big press where the thing is being, and we collect our data about the column and make sure we can image it correctly and get its dimensions. But the real-time control where the drone is actually flying and doing things is in this work evaluated only in simulation. So we've built this simulation technique system which is based on the Unreal gaming engine, so we can have pretty high fidelity 3D reconstructions. And then we can fly one or multiple drones in that setting, modeling different kinds of sensors. And this simulator though, the control actually interacts with the simulator over something called a ROS bridge, ROS being the robot operating system. So this would actually port over very easily to an aircraft because ROS is one of the standard ways of controlling a real aircraft, right? So the control software wouldn't really change. What would mainly change, I would say, that I'll show you results saying that we're able to reconstruct things to 3D to 10 centimeter accuracy and all of that. But that is assuming that these LiDAR noises and UAV pose noises are Gaussian, right? But in practice, of course, they're not Gaussian, so it remains open that exactly what accuracies which we would get if we were experimentally flying. I will say that the whole system that presented, though validated in simulation, can actually be tested by peer in practice, because the lower level control, which is responsible for safety, is actually already been experimentally tested by Professor Muller at the Richmond Field Station. So if we take this drone and actually fly it at the big press, there won't be any accidents. What will at worst happen is we will not get data of the quality that we need, right? So in that sense, it is very ready for testing by peer. So this is actually saying, showing you the high-level control, right? So basically what the high-level control does is that it evaluates the frontier between the known and the unknown. You can see that with the gray boxes, right? The gray boxes are unknown, the white boxes are known. It establishes the frontier, and then in that frontier, it tries to go, right? It picks these sort of points where it can gather the maximum information about what is unknown, right? And then uses an algorithm to randomize amongst them and pick a sequence, to pick a trajectory that will maximize what we call the volumetric information gain, right? That the set of unknown cubes that will be imaged if we fly this path, right? And so that's the outer loop control. And then the inner loop control is the higher frequency control, where essentially what goes on is, there's this information from the LiDAR or a depth camera, which is on a single image basis, right? The previous thing runs on the whole 3D reconstruction, but this lower level control runs on a single image. So it takes this single image and breaks it up into these collision-free pyramids, and then chooses amongst them the one that best approximates the direction that's being sent by the higher level control, right? And this is the sort of interaction you'll see here. If this video plays, let me see if it's playing. It's not playing. So, okay, now it should be playing, right? So this is running on the Jefferson. So you see the high level control is given that as an MPV, right? That's the green. And then you'll see the red is actually the path that's executed, right? That is coming, this is the amendment produced by the low level control. And that coarse 3D reconstruction that's going on is actually that volumetric reconstruction, right? So that's not the high fidelity reconstruction that will be used to look for cracking and spalling and all that sort of thing, right? That's just the reconstruction that's being used to guide the search and to ensure that everything is imaged at least to the specified resolution, right? So in general, of course, the point cloud will be created at a higher resolution. Okay, and then so this you can see, the whole trajectory that actually emerges for this church, right? And sometimes the drone is flying low, sometimes the drone is flying high. We can see the same thing here, actually in a different angle. You would say that's the reconstruction that's actually produced offline, right? You process it, you can see that it's a pretty good reproduction, right? And you can see sometimes, if I play that trajectory, you'll see sometimes the drone goes low to image the base, and then sometimes it goes high and goes to that end of the room and that end of the room and that sort of thing. And you can see the deviations between the red and the green that's actually produced by the lower level control, right? This is the same kind of idea for the railway viaduct, right? So by looking at these different shapes, at least in simulation, we're trying to establish that yes, we can do different shapes, right? And so now it becomes possible to actually, sort of have this autonomy, because I think this different shape, I'm not a structural engineer, I'm just trying to learn that structural engineers don't want everything inspected to the same resolution, right? The previous talk was giving me a distinct sense of that, right? And that's why it's important to be able to consider variable shapes and to be able to specify resolution as an input to the imaging. This is my, I think, last slide. So we try these things, and these are the measures that we collect, right? Of course, it would be important to find out what we get if we're actually flying experimentally in flight. But you can see, like yesterday, Richard Henninger from Caltrans was saying that, the issue with the Skydio stuff is that it's too slow, right? Now, this is a simulation. I don't know if this is fast enough, but at least we started collecting the right measures. What's the total flight length? Will the drone have enough battery to execute a flight length like this? How much time is the flight taking? How will that compare to a Caltrans pilot doing the same flight, right? So we started collecting all those measures. You can see that, completeness here goes to 1, which is the way we want it. And you can see the kind of resolution, that we specified, and the kind of accuracy we are getting in the error in the offline 3D reconstruction, right? But I wouldn't set much store by these sort of accuracy numbers here, because this is computed in an average over everything, right? So if I'm imaging this thing, I'm counting errors imaging that wall just as much as errors imaging that place where the floor meets the wall, right? And as a colleague of mine likes to say, that's much more important, where the floor meets the wall, because buildings leak at the interface of contracts, right? So it remains to be seen that if we really specify where exactly one wants high resolution, what kinds of errors we'll actually get. So I think I'll just stop here. That we've tried to design a more autonomous UAV-based digital asset management technology that images to a specified resolution, and we've come up with these measures: completeness, reconstruction error, flight distance and time, and we've done them in simulation. And I feel like, here's what I'd like to be able to do next with Pierre. I would definitely like to be able to fly this stuff at the big press, right? Because now that we've built this hierarchical control, we know nothing is going to hit anything. Right? That's been pretty well tested. So now we want to actually move on to see whether we can get data of a manner that says to an organization like Caltrans, you can actually push a button and have this thing fly. Right? That's the vision we're moving towards. And then, of course, to speed up inspection time by embedding inspection intelligence into the autonomy, which I think we should be able to capture as the resolution of imaging. Right? So here's a BIM model or a 3D model that's now annotated with what resolution I want where. Right? But this remains to be seen, and it was kind of driving my questions to the previous speaker. I'll stop here. Thank you very much for your attention, and it's always a pleasure to be at this meeting.
We have time for a quick question or two. I have a question.
Yes.
So you're generally talking about one autonomous drone. If you have a large structure to cover, have you thought about interactivity between multiple drones? You must have thought about that. And how that would be handled.
Yes, so I did a bunch of work for the Navy on sort of surveillance technologies with multiple aircraft. Microphone. For the Navy with multiple aircraft. So here, this is why we're working with that volumetric thing, which even for a large structure isn't a lot of data. Right? So that map of what is known, what is unknown, what is observable, what is unobservable is something that can be shared in real time between a fleet. So I can put that in the cloud, I can connect them all to the cloud, and so they can use that to continuously divide up what they do.
I mean, you could envision after an earthquake a very large structure.
Yes.
You want to learn about it quickly.
Yes.
You don't want to cover it with one drone over hours. You want to get multiple drones.
Yes. But I feel like, what I would like to do though is experimentally fly the thing first with one aircraft, move from simulation to reality, and then the multiple drone stuff, I think we would then try very nicely in simulation.
Very good.
Before we,
Thank you very much.
Thank you.